So we'll start with forward selection and feature ranking. So yeah, feature selection again. So again, those are, no, I'm sorry, this one in this direction, sorry. So we start with forward selection and feature ranking. So forward selection, the general idea is you have as input a target dimensionality, which should be smaller, of course, than the original dimensionality. And since we are in the supervised scenario, you have training set. Yeah, so you have a training set of n-dimensional feature selection, feature vectors, and labels to all those training vectors. So the target variable is termed C here. And the basic approach is you compute some quality measure, which is determined as termed as Q here, for each dimension. So this quality somehow reveals how the feature di is suited to predict the target value. So it somehow reveals the correlation of the feature to the target value. Yeah? And you just compute that for each feature, then you sort the features, the dimensions, and just take with respect to this quality measure, of course, and then you just select the k best ones, yeah, because you wanted to have a k dimensional feature space, so you just select the best k dimensions. Very simple. If you have a quality measure, that's very simple, and that's why yeah, the basic assumption is also quite simple, because you assume attribute independence. So there is you assume that there are no correlations between features, and just looking at each individual feature gives you the optimal k-dimensional feature space. And you know, of course, that in the scenario we had here, look at this one here, in this scenario, that of course fails, yeah, obviously. Okay, so but anyway, that is how you do that, and the key concept obviously is this quality measure here, this Q here. So the question is how to suitably predict the correlation between a feature and the class attribute. And there are different, and you want to do that model agnostic typically. So there are a lot of statistical methods that usually rely on distributions over the feature values and the target value. Yeah? And you want to evaluate how strong is the correlation between the distribution of the feature and the distribution of the target value. Yeah? And sometimes also how good does the splitting the values in the corresponding feature separates the values in the target dimensions. That is actually the same question with the correlation here, and that somehow reminds you probably on this all those measures we had for splitting a node in the decision trees, and that's why actually those methods can be used here again. So how to measure the distribution? So we want to compare the distribution over a given feature and the target feature, the target attribute. So yeah, how to measure those two different distributions? Well, for discrete values, you just determine probabilities for value pairs. That's easy to do. For real features, you can of course discretize the value space, then you are again in this discrete case, or you can use probability density functions like Gaussian distributions, typically what you do. Yeah? And here is the example quality measures. You probably already know from KDD1 decision trees, so information gain, mutual information, chi-square statistics, all those things can be used. Okay, so have a look at those things here. First of all, information gain. So information gain is based on entropy, and the basic idea is we want to evaluate the class discrimination in each dimension. Yeah, this is used in one of the algorithms for decision tree building. Yeah. And once again, we use entropy as a measure of the pureness. So entropy measures the pureness of a data set with respect to a given class label. Yeah. And the entropy can be just computed as this one here. It's so PCI is the relative frequency of class CI in the training set. Yeah, so you have a data set, a training set with labeled data, and of course you can compute the frequency of class CI in this set here. Yeah, and then you just take this frequency times log of this frequency and get the minus and sum that up. Yeah, and what does it do actually? So here you see the entropy value plotted with respect to the frequency value, and you see if the frequency of your class or of your classes actually, because you sum up over all classes, if the frequency of all the classes are 0.5, meaning that there is absolutely no pureness, everything is just spread over, you have a 50-50 relationship between, if you have two classes, you have a 50-50 relationship. So this is the worst case. You don't want to have that, of course. Then the entropy is 1. And in the best case, where you have either one class 100% and the other 0, or the other way around, the entropy is 0 in this case, in those cases. Yeah, so you want to have you want to be at the tails of this plot here, either a class distribution of 0 or of 100%. Yeah, because in this case you have 100% of one class and 0% of the other classes. In this case, the entropy is 0. Yeah, so worst case entropy 1. Best case entropy 0 means pureness is the highest. So here is an example. So let S be a collection of positive and negative samples. So we have a binary class problem, and the class labels are plus and minus, positive and negative. And then we want to compute the entropy for some given splits here. And in that case, we just take the frequencies. Sorry, the frequencies of the positive examples minus the here, of course, minus the frequencies of the negative examples, and then we can compute the entropy here. Yeah. So here are some example distributions. So this has a distribution of 9 positive examples and 5 negative examples. You see the entropy here can be computed as follows, which ends up in almost 1, but not perfectly. So this one here, not perfectly 1. So this is not a good entropy value, obviously. Yeah. So this here is the worst case. You have a 50-50 distribution, 7 plus 7 minus. So in that case, as we examined before, the entropy is 1. So you don't want to have that. That is the perfect case, because in that case you can really split the whole thing in this dimension, because 14 are plus, 0 are negative. So in that case the entropy is 0. Yeah, so entropy 0 means that all samples are in the same class. So you have 100% pureness, and that's what you want to have actually. So how can you use that now? You can use that in the information gain value that evaluates one specific feature relative to the training set S, and actually what you measure here is the gain reduction in S due to splitting the training set S along the dimension or along the feature di. Yeah, so you take the entropy before you split, this one here, minus the entropy of all the splits you get if you split along a given dimension di. Yeah, so you split your training set along the value distribution of di. You get splits Sj, and then you sum up the entropy of all those splits Sj, normalized by S, and subtract this sum here from the entropy of the set if you didn't split. Yeah, and well, how should that look like? Well, in the best case, the entropy before is 1. In the best case, the entropy after the splits, all the entropies after the split are 0. So the whole sum is 0. So you have 1 minus 0 is 1. So the higher the gain, the higher the value of the gain, the better the splits are. Yeah. So you want to optimize or maximize the value of this gain here. Yeah. The other way around, if entropy is small and the sum is more or less the same like this entropy here, you get a small gain, meaning that the splits did not really improve the entropy before. Yeah, so you want to maximize this gain value. How to get these splits actually? Well, for nominal attributes, you just use the attributes values as we saw it in KDD1 with decision trees for splitting. So each possible value because you have just a finite set of values here, nominal attributes. So each possible value in the feature defines a split, and each split contains all objects having exactly this this value in the corresponding feature. For real valued attributes, you may have an infinite number or a possible infinite number of values. So in that case, you determine the splitting position by setting a value, fixed value, and then split into all objects having values smaller than this fixed value of b, and all objects having values above that value in the corresponding attribute, of course. Yeah, so you end up in 2 splits, S1 and S2, and then you can again compute information gain. So here's an example. The question is, which dimension is better, humidity or wind? So here you see that the original training set is not very good. You have 9 plus and 5 minus, so the entropy we saw before is 0.94. And then you have, for example, 2 possible values in humidity. So you probably recall this is the example from the KDD1 slides. So we had in that case 2 possible values for humidity, high or normal. And if you take only the samples from the original set S here that have high, you end up in 3 samples that have a positive class label and 4 that have a negative class label, giving you an entropy of this one here, and the normal thing gives you this one here. And then if you compute the information gain, it's 0.15, and you can do the same thing here with wind. In this case, you get a gain of 0.048. So in that case, humidity would be a better split. So large values here are better, of course.